Welcome to the 24th lecture of graph theory. In the last class, we had introduced the class of perfect graphs and we had considered several examples of perfect graphs. First was bipartite graphs and complements of bipartite graphs. Then we considered line graphs of bipartite graphs, complements of line graphs of bipartite graphs, and comparability graph, their complements, comparability graphs. And finally, we had reached interval graphs. So, we introduced the class of interval graphs as the intersection graph of a family of intervals on the real line. That means, for each vertex we will be able to assign an interval on this real line such that two vertices are adjacent if and only if the corresponding intervals intersect. So, if for a given graph such an interval representation is possible, if we can find intervals on the real line for each vertex of the graph such that two vertices are adjacent if and only if the corresponding intervals intersect, then we say that the given graph is an interval graph. These interval graphs are also very useful graphs. In several practical applications it arises. So, of course, so they are defined because of their usefulness. And now, but our intention here is to verify that these interval graphs are in also perfect graphs. That means, any interval graph is a perfect graph. To remind you what was a perfect graph, it meant for the graph and each of its induced subgraphs. Not only for the graphs, we have to also consider in every induced subgraph for the graph the usual inequality chi of g greater than equal to omega of g. That means, the chromatic number greater than equal to the clique number should become equality. That means, chromatic number has to be equal to the clique number, not only for the graph, but also for each induced subgraph of the graph. Then we have explained why probably this slightly strange definition arises, because otherwise the question was not very relevant, right. That is why we had to introduce this induced subgraph thing also in it, in the definition. And then we verified in most of these cases induced subgraph also, for instance, in the case of bipartite graph, line graphs, in most of the cases we have seen the induced subgraph also belong to that class. Therefore, as long as we prove that the clique number is equal to chromatic number was enough. It is not true in every case, because some cases the general properties may not that is there for this entire graph may not hold for an induced subgraph. Therefore, it is not enough to always consider just for the entire graph the chromatic number and the clique number. Some cases we have to go into the induced subgraph and prove it. Here again, interval graphs have this property that if you consider an induced subgraph, it is again an interval graph. Therefore, we do not have to worry too much about the this special property being satisfied for every induced subgraph. So, we will just prove that the chromatic number is equal to clique number for any interval graph G. This is our next aim. So, how do we show this thing? So, we will consider this interval representation, because it is an interval graph, we have an interval representation. So, let us say this is the real line, and see I will mark an interval like this. So, this can be typically okay. This can be the interval representation of some graph. Now, what we do is we search from the left end, that means we can come from this side, and we find out the first interval graph that opens. So, we are going to prove, our intention here is to prove that the chromatic number of this graph is equal to the clique number. As we all know, this is always true for any graph greater than or equal to omega of h. Now, it is enough that if we find a coloring of this graph such that the number of colors used in the coloring is equal to the clique number. This is what we are going to do, that will imply that this is in equality. So, for that matter, so therefore, we are going to color the graph. So, how am I going to color? So, first I will search for the first opening interval, the first starting interval. It does not mean that the interval which starts first should end first, that is not necessary. So, we just find out the starting interval and give it a color, and then we look at the second starting interval and we will give it a color in the greedy way. What is the greedy way? We will look at its neighbors which are already colored. Other than we have to avoid those colors of course. Now, among the remaining colors that we have already used, we will, if anything is left, we will take the lowest numbered color, lowest color. Otherwise, we will go for the next color, that is the plan. That means, we will reuse a color if possible. Otherwise, if only in the case of reusing not possible, then only we will take a new color, So, this is the greedy strategy. We are very familiar with it. In the case of in the earlier, when we introduced the coloring, we had introduced this concept of coloring number, degeneracy, all those things, right. We consider certain ordering, and that is how we initially proved that maximum degree plus 1 is a upper bound for the chromatic number, and then later we told that in many graphs it can be much smaller, because if we consider the correct ordering, we may see that the ordering may allow us such an arrangement in such a way that, for instance, whenever see a vertex, its lower numbered vertices with respect to that ordering may be much smaller than its maximum degree. That's what that plus 1 was the so that was the degeneracy, that plus 1 was the required number of colors, we called it coloring number, right. So, the same strategy here, but here see how it works, because in those cases we were not guaranteed that we will get an optimum coloring. The number of colors that we end up using may not be optimum, but here it will become optimum. Why? Because of this reason. So, we are taking this is the ordering we are considering is with respect to the arrangement of the intervals, the left endpoints, and we will consider the intervals or the vertices in the order in which the left endpoints of their intervals appear when we scan from left to right and on the real line. So, this is considered first, then this is considered, and of course, the coloring strategy is greedy strategy, and maybe third we will consider like this. Now, we want to say that. So, when we color the ith interval, suppose we are coloring the ith interval. So, okay, we will in the entire process might have used say k colors in this way. Now, there will be an interval, say the ith interval, ith vertex, which got the color k, right. This got the color k. How did it get the color k? Because there were k minus 1 neighbors of it, which were colored differently, and we had to take the kth color. That is why it happened. You see, it starts here, the ith interval starts here, and it had to be given the kth color, this interval. So, the reason, so now how will their neighbors be? Because all the neighbors which are already colored started from somewhere here before this, right. See somewhere here, right, because we are scanning from left to right. So, therefore, we will see this neighbors of this starting from here. But if a neighbor started from here and ended here itself, then it will So, a vertex started somewhere before this and ended before it, then it will not be a neighbor of it, because these intervals are not intersecting, right. So, only a interval which intersects with it will be a neighbor. So, any neighbor of this which is already colored, which start before this, but end after this, after this point, right. Maybe it can end here or it can even go further, but the key point is all those intervals corresponding to the neighbors of this, which are already colored neighbors of this, has to pass through this right point which I have marked right. So, because they start before and have to end before, because it is a neighbor of it, right. So, if all of them goes through this point, then what does it mean? They all intersect with each other, pairwise intersect, because this point is in all of them. So, it is a clique, and this ith vertex itself is part of the clique. So, that means we have this k minus 1 plus 1 vertices belonging to a clique corresponding to this red point, right. So, we have a k clique there, and by assumption we have only used k colors. What does it mean? So, we have colored the interval graph using k colors. On the other hand, there exists a k clique in the interval graph. So, the chromatic the clique number can only be bigger than this k, right, because there is a k clique. Bigger, it can be bigger than equal to, but it cannot be strictly bigger, because if it is strictly bigger we will need more colors also, but we are saying that we have used only k colors. So, how is it possible? So, we conclude that k is indeed the chromatic number also, the chromatic number is indeed the clique number also, that we get that chi of g equal to k equal to the clique number, right. This is what we get, this is what we wanted. Now, for an interval graph, its chromatic number and clique number is equal. Any induced subgraph of the interval graph is again an interval graph, there also the chromatic number and clique number will be equal, therefore, interval graphs are perfect graphs. So, this is the reason why interval graphs are perfect graphs. Now, of course, as we were checking in all the previous cases, whether whenever we considered a class, we also considered whether they complement, the class of the complement graphs was also perfect. Here also we will do that. What about co-interval graphs? What do we mean by co-interval graphs? Just that it is a co-interval graph is a graph whose complement is an interval graph, that is all. So, now we know how to check this. How do we do that? We just have to consider the independent set of the interval graph, because this independent set of the complement interval graph will become the clique number of the co-interval graph we are considering, right. Like we have done it before also, in the case of all the previous classes we have done this thing. Alpha of its complement will be the clique number of the original, right, the co-interval graph we are considering. Now, we have to show what will be the chromatic number convert to in the complement interval graph. The chromatic number is a covering using independent set. So, it will become a covering using the cliques in the corresponding complement graph, that means in the interval graph. So, that is called a clique cover number. In the complement, the chromatic number becomes the clique cover number, because we are trying to cover using cliques all the vertices, right. We want to cover all the vertices of the graph using as small a number of cliques, that is what the clique cover number. And then what about we want to show that for an interval graph, the clique cover number is equal to alpha, the independence number, that is the stability number, the biggest independent set size. You know, if you show this thing for all the induced subgraph also, this will be true, which means that for the complement the chi of g is equal to omega, the omega of g, that the chromatic number and the clique number will be equal, and for all the induced subgraphs. So, let us show that for the interval graph this is true, that means omega the clique cover number is equal to the independent set. This is the method. We again consider our real line, and then we first consider the interval. This time we consider the interval which starts which ends first we scan from left to right, we look at the interval corresponding to the earliest closing brace, that means which the interval which closes first. So, there can be several things which starts before this thing, but this is the one which closes first. It does not mean that it is an interval corresponding to the earliest starting bracket, it can be, see, this may be that, right, this may be that. So, all these things may go further, it may be this may go like this may go like this, or this may go like this. So, just that we are considering the interval with the earliest closing brace, the first closing brace, that interval we will add to our independent set, right, we will add to our independent set that interval. This is what we are going to do first, right. And now what we do, we will remove all the vertices which pass through this point, which cross through this point, because this is the first closing brace. Anything which starts before this thing has to go further, right, because they do not close before or before this. So, they all have to at least touch this or go further. So, this point P1 we can define the clique corresponding to this point, means all the intervals which cross through this point has to be adjacent to each other in the graph. That means they intersect, the intervals intersect with each other, therefore, they correspond to a clique in the graph, right. So, therefore, that clique we can collect, let us call it K1, the first clique. So, that we put one in the independent set, this is an independent set we are forming, this namely this interval which ended there, and then we also collected all the intervals which passed through that correspond to a clique, and that is added to the clique cover. So, we are going to construct a independent set as well as a clique cover for the graph side by side. So, one in the independent set, one vertex in the independent set, a clique in the clique cover number, like that we keep adding and show that by the end of the procedure we will get an independent set and a collection of cliques, so that the cardinality of both the sets are equal. That means, the number of cliques in the clique cover will be equal to the number of vertices in the independent set, and this collection of cliques will cover the graph, and moreover we will show that right, cover the graph, that sort, because that is enough. Why? Because as we see, the clique cover number has to be always greater than equal to the independent set, and what we are demonstrating is a clique cover whose cardinality is equal to the cardinality of some independent set. So, the maximum independent set cannot be more than this, right, because if it is more than the clique cover, we will not get a clique cover of this cardinality, right, because the clique cover number has to be at least as much as the cardinality of any independent set, in particular greater than or equal to the maximum independent set. If we demonstrate a clique cover whose cardinality is only equal to some independent set, that is enough. That means that the independent set we have got is also a maximum independent set, right. That is what we are going to do. So, we got one here. After that, we remove this interval as well as all the intervals corresponding to this clique. So, we just remove it. That means, now we will see, after the removal we will see a some intervals are removed, right. Now the remaining intervals will be seen here, right, as if nothing has happened, because again it is an interval graph after removing something, just that we removed one vertex and added it to our independent set, and removed all the cliques, all the vertices which pass through the end point, the closing end point of that interval, which formed a clique, right. So, that was added to the clique cover. Now, the same thing we will do from the remaining interval graph. We pick up the first closing brace, maybe this is the first closing brace and it may correspond to this, right, and then we will add this to our independent set. This will be the second vertex in the independent set, and then corresponding to this point we can collect all the vertices which pass through this. In particular, everything which starts before this thing has to pass through this point. This will correspond to a clique, and this clique is added to the independent set. Now, you remove all the vertices now, right. So, so they which belongs to the clique, right. So, now you see that by this procedure, by the end of it you will remove all the vertices, because you see whenever I am removing the vertices, we are sure that the starting opening braces of before this and all the so the we are not arbitrarily removing anything, right. So, each point will corresponding to which we remove this thing, we are actually removing the intervals which starts before that and ends after that, and because we get points across this thing. So, every vertex will be every interval will be covered by this clique. So, it is indeed a clique cover number, and what we are making is indeed an independent set, because we added something, a closing brace, and then we know that we have removed all the vertices which started before this. So, any vertex which is left starts only after that point. So, it will be in fact independent of the already added vertices, because that will start strictly after the last end point of the last interval that we added to the independent set. Therefore, we are going to get an independent set. So, we see that here we will indeed get a clique cover whose cardinality is equal to the cardinality of the independent set we make by the end of the procedure, right. So, therefore, here alpha of g is equal to k of g, the clique cover number, that is it. Okay, fine. So, this is the proof for that the complement of an interval graph is also perfect. The final thing is a very well known class of graph called chordal graphs. So, what are chordal graphs? So, it is defined like this. Again, these are also coming from application because of their usefulness in practical situations. So, the chordal graph means you consider a graph and you consider a cycle in it. Suppose the cycle is of length 4 or more, say this is a 5 cycle here, then we should get a chord like this, a chord for that, right. This should be a chord here. It should not happen that, or now we see a 4 cycle here, we should get one more chord here, right. This is a chord, right. So, this is so that in other words there should not be any cycle in the graph of length 4 or more without a chord. No chordless cycle of 4 or more should be there. So, a cycle, if this is a cycle, so and other than the adjacent vertices in the cycle in this order, nothing else is connected, it is a chordless cycle. So, a chord for the cycle will be like this, for instance, right. This is a chord, this is a chord. So, if no chords are present, then it is a chordless cycle. If we consider the vertices of the cycle and take the induced subgraph of that, then if it becomes a simple cycle when you take the induced subgraph, that is a chordless cycle, or it is also called an induced cycle. In the perfect graph literature, it is sometimes called a Hall if the number of vertices participating in this cycle is more than 3, right. 3 cycle is a triangle, it's not a Hall in fact. So, so in other words, we do not allow any halls in chordal graphs, right. So, we do not allow that. So, in other words, any cycle of length 4 or more should have a chord, or any induced cycle in the graph has to be a triangle, no induced cycle of length 4 or more. This is what the chordal graph is. So, it may look like the definition of the chordal graphs does not seem to imply to tell too much, because it is talking about the cycles, it is talking that okay, there is no induced cycle of length. How does it help us to prove that it is perfect or not perfect, whatever, right. Does it make any sense? Is it connected to the chromatic number, or is it connected to the clique number somehow? So, but it so happens that the chordal graphs have so many properties. Just this simple looking fact that there are there are no cycles of length 4 or more without a chord, no chordless cycle of length 4 or more will allow us to infer a lot, right, about the chordal graphs. So, let us look at some of the immediate properties. we have studied what are the separators. So, let us consider this, suppose we have a caudal graph G and we consider a minimal separator S of that. What do we mean by minimal separator? It is a collection of vertices. If you remove this set of vertices, the graph will get disconnected. That means, there will be at least one piece here which we can call G1, at least some piece here G2, maybe there are more also G3, right. But the point is, if you remove any subset of this vertex, we cannot disconnect the graph. In that sense, it is minimal, that is the point, right. In that sense, it is minimal. So, you cannot, no proper subset of this can separate the graph. Now, if we consider a minimal separator of the graph, so that means at least 2 vertices. So, because it is a minimal separator, we also know that every vertex has to be adjacent to both sides by at least one vertex, because you know, if there is a vertex here, suppose this vertex was not adjacent to this side, then you could have removed this portion and it will separate this part from the remaining, right. This we have seen before also. Therefore, every vertex should be adjacent to one vertex on both sides, otherwise removal of that, in fact to each component, otherwise a subset of that would see, if you, that vertex which is not connected to both sides can go along with some other components, and the remaining vertices themselves can manage to separate one piece from the remaining, right. So, therefore, so the minimal separators have this property. So, this is the minimal separator we are considering, let us say without loss of generality, there are this G1 and G2. And now, suppose it is, we want to claim that this is the induced subgraph on this S, if G is a caudal graph, has to be a complete graph. It should be a clique. Suppose it is not a clique, what can happen? So, suppose it is not a clique, then see, there are at least 2 vertices there, because if it is just one vertex, it is a clique. So, and moreover, is it possible to have some 2 vertices? It is not a clique, right. There should be 2 vertices such that they are not adjacent to each other. So, let this be the 2 vertices which are not adjacent to each other. We will mark it with red. So, yeah, so 2 vertices. Now, we know this has a neighbor here, this has a neighbor here, this has a neighbor here, this has a neighbor here. There can be equal the neighbors, but there are some neighbors. So, what we do is, here I will say this is x, this is y, this is a, this is b, this is our culprit vertices u and v. Okay. Now, we can see, because this is a connected component, from y to x there is a shortest path, there is a path here. Similarly, a to b also there is a shortest path. When I say shortest path, a and b can be equal, in which case the shortest path is that a to b, so the single vertex. Similarly, here. Now, we claim that, so among all the neighbors of v, so if we had considered this y to be y and x to be the shortest, I mean the closest such neighbors, that means their distance is minimized, then we see that then there will not be any more edge from here to here. So, we know that there will not be any more edge like this or like this, right, into the path, right. Why? Because we could have taken these 2 pairs as a shorter pair then, right. So, therefore, we can rule out these kind of edges. Also, because this is the shortest path, there will not be any edges of this sort, right. This kind of short circuits will not be there, because it is indeed a short path. So, that will not be there. And now, similarly, so of course, then x, v, u, y, such edges will not be there, because in that case we could have taken x and y to be the same. Similarly, the similar things can be told about it. These edges, this edges, this edges, this edges will not be there. Similarly, this kind of edges will not be there. So, this is indeed a this root, this one, this edge u x, and this shortest root here x to y, and then y v, and then v b, and this shortest root here, and then u a is indeed a chordless cycle or induced cycle in the graph. But then here 1, 2, 3, 4, 5, 6 vertices are there. It need not be 6 vertices. If x and y are same, then it may turn out to be something like u v x here, this is a here, because a and b can be same here, right. This a b, this x y can happen to be the same vertices. So, this will, and of course, you may ask, is it possible to have any chord of this sort, right, cross chord this way? No, it is not possible, because it is a separator here. It is not possible to have a chord of this sort, right, that is not possible. So, therefore, it is indeed a 4 cycle. So, we infer that it is not possible to have some u and v in the minimal separator S such that they are non-adjacent. So, every pair of vertices in the separator, minimum separator, has to be adjacent, that is what we say. So, we infer that in a caudal graph, any minimal separator S should induce a clique in a caudal graph. See, note that we have proved it by using the simple fact that in a caudal graph we do not have induced cycle of length 4 or more. That implies this, that any minimal separator S of a caudal graph should induce a clique in it. That is a good thing. How does it help? So, there is this concept of simplicial vertices, which is very useful in the study of caudal graphs. So, what is a simplicial vertex? So, in a graph, a vertex is called simplicial. So, this is a vertex. If you look at its neighbors, if they form a clique, if these neighbors form a clique, that means they are all pairwise connected. So, of course, including this, it will be a clique which is one more vertices, right. Such vertices are called simplicial vertices. So, here do you see in a cycle, do you see any simplicial vertex? No, definitely you do not have a simplicial vertex. That is why this, so this is, there is no simplicial vertex, because if you take this vertex, its neighbors do not form a clique. If you take this vertex, its neighbors do not form a clique. But on the other hand, if you take a tree, do you see any simplicial vertices? Yes, of course, if you take this leaf, see here its neighbor is only one, and then it is indeed a clique, right, one singleton clique. Or you can, for instance, you can see a graph like this, simple graph like this. So, here we have several simplicial vertices. For instance, if you take this vertex, right. So, this is a simplicial, neighbors form a clique here. So, this is a simplicial vertex, because its neighbors form a clique here, right. So, but this is not a simplicial vertex. Why? Because its neighbors are this, this, this and this, and this and this together do not form a clique. So, some graphs have simplicial vertices, some graphs do not have simplicial vertices. In a given graph, all vertices need not be simplicial vertices, some vertices can be. So, if all vertices are simplicial vertices, what does it mean? So, so you can right. So, then see in our case we are talking about caudal graphs. In the caudal graph, we will say that there will always be a simplicial vertex. So, this is what we want to prove now, right. So, in a caudal graph, the property that, how does it allow us, that the property of not having a 4 induced cycle of length 4 or more, how does it allow us to infer that there is always a simplicial vertex? So, in fact, we will prove a slightly stronger statement, which is not that there exists one simplicial vertex. In fact, most of the time there will be 2 simplicial vertices. In fact, there will be 2 simplicial vertices. Essentially, if the caudal graph is a complete graph, every vertex is a simplicial vertex, right, is not it? Right. So, if the caudal graph is not a complete graph, we will show that there will always two two simplicial vertices which are not only simplicial vertices which are non neighbors, in fact non adjacent, two vertices which are non adjacent and also simplicial. Such simplicial vertices will be present. That is what we are going to prove now. How do we prove this thing? So, let us say to prove this, we will consider an induction. So, for a small graph we can, for one vertex graph, so it is a complete graph, there is nothing to prove. For two vertex graph, right. So, it is obvious. So, like that smaller graph we can prove it for induction, for 3 vertex graph we can check. Now, let us say suppose you take an n vertex caudal graph. Now, for all smaller caudal graphs we know this statement. That means, if it is a non complete caudal graph, then there exists a pair of non adjacent vertices such that both of them are simplicial in the graph. So, now what do you do? So, this is a graph, this graph is given. So, there is this two vertices u and v which are non adjacent. So, therefore, there is no. So, if two vertices are there in the graph which are non adjacent, we can always find a separator for them, right, because it is non adjacent. Let us call it S, right. And if there is a separator, there is a minimum separator. We can always consider the minimum separator separating u and v. So, now we have two, we can consider two graphs. So, this side of S which containing u and the side of S which containing v, right. So, there can be other things which we can add to this part or this part. So, for instance, it may not be the total number of components that we are interested. So, there are at least one more vertex here because v is here, at least one more vertex other than S. Now, the question is what about, so we look for one, see this portion there is at least one vertex u. So, this portion there is at least one vertex v. So, what if we can pick up one simplicial vertex from this side and one simplicial vertex from this side? We know because they are on different sides of S, the separator, they are going to be non adjacent. If such simplicial vertices exist, then indeed our statement will be true, right. So, but is it guaranteed that we will get a simplicial vertex in this side? For instance, if I consider this graph, is it guaranteed that on this green side I will be able to find a simplicial vertex? See, we know that if it is a there are simplicial vertices, because it is indeed a caudal graph, a smaller caudal graph, we can apply the induction hypothesis, but there is a possibility that the simplicial vertex take, because it is just a caudal graph together, it may end up here inside S, right. But we know that okay fine, we have a caudal in simplicial vertex here, but then if it is a complete graph, this happens to be complete, then we could have taken any vertex, we could have taken this v itself, right, that will be a simplicial vertex, right. Now, or any other vertex on this side would have been enough. So, we can assume that this is as such not complete. Therefore, there are two non adjacent vertices which are simplicial in this part itself. So, if one of them is here, do not worry, take the other. So, and the other if the other happens to be here in this side, we are done, we got a simplicial vertex. Now, what if the other vertex out of this two non adjacent simplicial vertex is also here? In fact, it can also happen to be here, right, inside the clique. Is it possible? No, it is not possible, because this is where we are using our previous lemma, because we know that this is indeed a clique, right, this portion is indeed a clique, and we have this edge between them because it is a clique. So, but then we know that two simplicial vertices we have are non adjacent, we have two non adjacent vertices which are simplicial. So, if one of them is here, the other has to be outside this. So, that means it has to be somewhere inside this. So, we get one, indeed we will get one in this region. Similarly, we will get one in this region also when we consider the induction assumption on this portion. So, therefore, we will get a simplicial vertex here and simplicial vertex here, that will mean that we have two non adjacent vertices which are simplicial in the caudal graph. So, this is a slightly stronger property than we usually need. Usually we need only one simplicial property from simplicial vertex in a caudal graph, that would have been enough for most of the purposes. But then if you try to prove that we have one simplicial vertex, we will it would be a good exercise to try to prove that by putting an induction hypothesis that there exists for up to n minus 1 vertex caudal graphs, we have a simplicial vertex, one simplicial vertex, and then we try to extend the induction, take the induction forward, you will find it a little difficult. This idea that we are strengthening the induction hypothesis by saying that we have two simplicial vertices which are non-adjacent helps to take forward, because that is strengthening of the induction hypothesis which helps us to push it fast easier, right. So, there are some we had studied a classic example of such strengthening of the induction hypothesis to prove the theorem when we considered the 5 choosability of planar graphs, right. How in that proof also it was by a clever strengthening of the induction hypothesis that we managed, rather than what we put is inductively we assume what is more than required, because we just wanted to prove that the planar graphs of 5 choosable, we assume something much more stronger and then proved it, because when you strengthen the induction hypothesis, it so happens that we have more things to use, right, that helps us, but we have to manipulate it very carefully. This is another such nice example. So, this is also much easier, therefore, you can you should try doing the other way and try to make it work without this strengthening and see it appreciate such a thing, such a technique. And now, so we know that this simplicial vertex is always available in a caudal graph. This gives rise to the idea of perfect elimination ordering. Perfect, this is what perfect elimination ordering in a caudal graph. So, it is called what is a perfect elimination ordering. So, also it is called PEO as a short form, PEO, right, perfect elimination ordering. So, perfect elimination ordering is a sequencing of vertices in the following way. So, first vertex V1 will be a simplicial vertex of the caudal graph. Now, you remove V1 from the graph and then we consider, because we get a smaller caudal graph, because all induced subgraph of the caudal graph is again a caudal graph. So, we pick up V2 such that V2 is simplicial vertex in the remaining graph, and V3 is picked up after removing V1 and V2 in this caudal graph that remains. It will be a caudal graph because induced subgraphs are always caudal. So, we pick up the simplicial, we pick up a simplicial vertex V3 and so on up until Vn. Every time we will get a simplicial vertex, because in a caudal graph there is always a simplicial vertex. So, such an ordering is of vertices is called perfect elimination ordering. The property of this perfect elimination ordering is that if you write down V1, V2 up to Vn and then look at Vi, the ith vertex, and you look at the neighbors of Vi which are higher numbered than, that means if Vi is here, we look at the neighbors which are higher numbered than Vi. Yeah. So, those, what will you see on the neighborhood? Of course, because Vi is a simplicial vertex in the induced subgraph on Vi plus 1 to up to Vn. So, therefore, this is going to be a clique, right, that is the special thing. So, it is very much like when we considered the degeneracy or coloring number or anything, but here the property that we are looking is not that the higher numbered neighbors are small, but we are saying that the higher numbered neighbors will induce a clique. That means, Vi will be a simplicial vertex in the graph induced by Vi, Vi plus 1, Vi plus 2 up to Vn in the induced subgraph on the higher or equal numbered vertices. So, such an ordering is called perfect elimination ordering. So, in a caudal graph, as you can see, a perfect elimination ordering is always available, as is obvious, because in any caudal graph there is a simplicial vertex, remove it, the remaining graph is again caudal, because the induced subgraph of a caudal graph is caudal, we get another simplicial vertex, and this sequence of elimination, that will be a perfect elimination ordering. And now it is not very difficult to show that this is also a characterization of the caudal graph. This is a characterization of the caudal graph. So, I will leave it to you to prove that if a graph has a perfect elimination ordering, it has to be a caudal graph. So, that yeah, it will have it will turn out to be a caudal graph. It is not possible for any other graph, if a graph is not caudal, it is not possible to get a perfect elimination ordering. I will leave it to you to verify that. So, now we will go back to our main aim. So, this was all told in order to study the caudal graphs and get some ideas about the caudal graph, but then these theorems will also help us to prove that the caudal graphs are indeed perfect graphs. How do we show that? See, to show that the caudal graphs are perfect graphs, again we need not worry about the condition on induced subgraph, because an induced subgraph of a caudal graph is again a caudal graph, and therefore, if I simply prove that for any caudal graph G, chi of G is equal to omega of G, for induced subgraph also the property will hold, right. So, to show that a caudal graph is perfect, we just have to prove that the caudal graph, for caudal graph, the chromatic number is equal to the clique number. How do we show that? As usual, since chromatic number is in general greater than or equal to omega, we just have to show a coloring of the given caudal graph using number of colors equal to the chromatic as a clique number, or number of colors equal to some clique, the size of some clique, that is enough, because the chromatic number, if the number of colors used is only equal to the cardinality of some clique, it has to be the maximum clique, because if there is a bigger clique, then we could not have done it, right, because that bigger clique would not have allowed a coloring of the graph using a lesser number of colors. So, it is enough to show that the number of colors used is, we show a coloring with the number of colors used equal to the number of vertices in some clique, that is what we are going to do. We will use the notion of perfect elimination orderings to do this thing. So, we will consider a perfect elimination ordering of the caudal graph, say V1, V2, V3, V4, so on up to Vn, and then we first color Vn, rather than coloring V1, we will color first Vn, give a color. So, the same greedy strategy like we did for interval graphs we will use here. In fact, essentially the idea of the interval graph is being extended here. So, V1 will be given color number 1, say one color, and Vn minus 1 will be given the color, if it will see whether its Vn is a neighbor of not, if it then we will use the second color. And in general, when I am coloring Vi, after coloring all the higher numbered vertices Vi plus 1, Vi plus 2 up to Vn, suppose I have colored and we consider Vi, what I do is I consider its neighbors which are already colored, that means neighbors which are higher numbered than this, and then see the colors which are already taken up by its neighbors, and then use a color which is available, which is the lowest color available from the pool. That means, if some color is unused, then among the unused colors we will use the smallest. If no color is available up to now among the pool which is up to now used, then we have to go for the new color. That is again same greedy strategy we are using. The only thing we have to show is the number of colors used is only equal to the cardinality of some clique. How do we show that? Suppose k as usual, k be the highest number of colors used. So, there is a place, there is some time when the k appeared for the first time, right. So, suppose this Vi, ith vertex used k color, the color number k for the first time, that is the largest color we have used. So, now look at its higher numbered neighbors. So, what do you see? Because higher numbered neighbors, because it is a simplicial vertex in that graph. So, you see this is going to be a clique, right, this is going to be a clique and this is going to be a clique. Now, so k colors are used. Of course, the k, if I had to use the kth color, that means all the colors below it 1, 2, 3 up to k minus 1, all of them are already used up by the neighbors of this thing. That means exactly k minus 1 higher neighbors are there here, right. So, otherwise how can they use up all the colors? So, now these neighbors form a clique, and this, if you add to it, you will get a k clique, right. So, you have demonstrated a k clique where k is the maximum number of color used, the maximum color used. So, therefore, we see that chromatic number of this graph is equal to k equal to the cardinality of this clique, which essentially means that it has to be the cardinality of the maximum clique, right, because there cannot be a bigger clique, and in that case we could not have colored with k colors, right. So, it happens that for the caudal graph, chromatic number is equal to the clique number as we want. So, therefore, caudal graphs are perfect. Now, the final thing we want to verify is whether the complement of caudal graph is perfect or not. So, the same strategy. So, we just have to figure out whether what is the so called co-caudal graphs, the complement of a caudal graph. So, given G be a co-caudal graph, now G bar is a caudal graph. So, what do we have to show? To show that, so again if it is a co-caudal graph, induced subgraph is not a problem because they will again be a co-caudal graph. Therefore, we just have to prove that for a given caudal, any co-caudal graph, the chromatic number is equal to the clique number. So, that will amount to showing that in a caudal graph, the clique cover number is equal to the largest independent set size, that means the independence number, the stability number. So, as we did in the case of interval graphs, we will do the same technique here. So, what we do is we start from a simplicial vertex, we take a simplicial vertex V 1, and then we will remove. So, we will add V 1, the simplicial vertex, to the independent set that we are creating. We will collect some independent, create an independent set by adding vertices one by one to it, and then along side we will collect some cliques, and by the end of this procedure we will show that what the cliques we have collected is forming a clique cover number, and the vertices we have collected is an independent set, and their cardinality is same. So, we have a clique cover whose cardinality, the number of cliques in it, is equal to the cardinality of the independent set size. So, some independent set size, that is enough. Therefore, the clique cover number has to be strictly greater than or equal to the maximum independent set size, right. So, this has to be a maximum independent set, and that has to be a minimum clique cover then. So, that will prove the same thing as we are repeating the arguments that we have done for the last the interval graphs or many of the earlier cases here. Here slight technique is slightly generalized from the interval graph. We are just picking up a simplicial vertex first and adding it to this thing, and then what we do, we look at, because it is a simplicial vertex, its neighborhood forms a clique, we remove all the neighbors along with that vertex, that together will form its neighbors and itself, that simplicial vertex will form a clique in the first clique in the clique cover number. Now, in the remaining graph, it is again a caudal graph, we again have a simplicial vertex, we can collect the vertex and its neighbors and add the second clique to the clique cover we are creating, and this vertex itself can go to the independent set, right, we are going to create. See, this new vertex I am adding, and this V 1 and this say V 1 V 2 will not be adjacent, because you have already removed all the neighbors of V 1. So, this V 2 will not be a neighbor of that. So, therefore, V 1 and V 2 are whatever I am going to add to the set S is going to be independent. Every time I am adding a vertex to that, I am removing all its neighbors. So, what I collect there is going to be an independent set, is very clear. Now, on the other hand, similarly, every time I am collecting the neighborhood of my vertex is a clique, and along with the vertex it is forming a clique, and by the time I finish off all the vertices, I have covered all the vertices, because I am removing from the graph only the vertices which go along go inside some clique, because I am always when I am removing, I am making sure that I am removing a clique. So, therefore, I have this k 1, k 2, k 3 etcetera covering the entire vertex set of the graph. So, it is indeed a clique cover of the graph, and the number of cliques that we have collected here is indeed equal to the number of vertices I have collected in the independent set. So, this S and this is equal, and then which means that this clique cover, this is a clique cover number, is indeed the minimum, because it is equaling the cardinality of an independent set, right. And this S has to be a maximum independent set, because it is equaling the cardinality of some clique cover, right. So, they are both minimum clique cover and the maximum independent set. So, we have shown that in the caudal graph the maximum independent set size is indeed the clique cover number, which essentially means that in the co-caudal graph the clique number, the maximum clique cardinality size is equal to the chromatic number. So, co-caudal graphs are also perfect graphs. So, we have considered several subclasses of perfect graphs now. That means several well known graph classes and their complements. We have showed that not only the graph class, also the complement class is also perfect. So, this essentially is a common theme, common property for all perfect graphs. That means, if a graph is perfect, its complement is also perfect. We will give a proof for this theorem in the next class, and we will explain it a little further, how we can understand it better, right, in the general point of view. How we discussed all these things, this many several this many classes of perfect graph is to illustrate that there are several important classes of graphs which are indeed perfect. So, we will continue with perfect graphs in the next class. Thank you.